Welcome to this explainer. Today, we're doing a really cool, in-depth dive into exactly how Linux manages its data behind the scenes. You know, if you've ever worked with a server, you quickly realize that an operating system is only as good as the foundation it's built on. And honestly, understanding that foundation completely changes the way you look at computing. So let's jump right into this.
Okay, think about this relatable IT mystery for a second. Why is it that Windows machines historically needed constant rebooting, but Linux servers, they can literally run for years without ever being turned off? And even wilder, if a data center suddenly loses power, how does Linux magically recover so many files completely intact when the lights come back on? Well, the answer to both of those questions doesn't actually have anything to do with the hardware. It is entirely about the brilliance of its file system.
To uncover these secrets, here is our roadmap for today. First, we'll cover the file system basics, then dive into the magic of inodes, followed by deletion and stability secrets. After that, we'll look at common Linux file systems, and finally, monitoring and enterprise storage.
Let's start with Section 1, the file system basics.
So, without a file system, your hard drive is basically just a chaotic wasteland of raw bits, right? It desperately needs a librarian. And this brings us to the really mind-bending philosophy of Linux. Everything is a file. Unlike other operating systems, Linux treats your hard drive, your USB stick, your mouse, and even your network card exactly like it treats a normal text file. By unifying the hardware and software management under this one single model, Linux achieves absolutely incredible modularity.
Now, if you're coming from the Windows world, you're probably super used to seeing multiple drives. You know, a C drive, a D drive, maybe an E drive. Well, Linux completely flips that upside down. In Linux, there's only one unified tree. The whole thing stems from the very top, which we call the root directory, represented by just a single /. So no matter how many physical hard drives you plug in, they all just become little branches extending off that one massive tree.
Which actually brings us to a concept that trips up a lot of beginners, and that's mounting. Mounting is really just the act of attaching a physical disk partition to a specific directory path on that giant tree. For instance, if you use the mount command to link a brand new hard drive to a folder called /data, anytime a user opens that /data folder, they probably think they're just clicking into a normal directory. But under the hood, the file system has seamlessly bridged them over to a completely different physical hard drive.
Moving on to Section 2, the magic of inodes. You know, you could use Linux for a solid decade and never even hear the word inode. But it is arguably the most important concept in the entire system. See, Linux doesn't actually use file names to manage files. File names? Those are just convenient little illusions created for us humans. What the system actually cares about is the inode number. Every single file gets its own hidden ID badge containing all its metadata. We're talking the size, the permissions, who owns it, the modification time, and crucially, the exact physical block locations on the hard drive.
But let's break down what that actually looks like in action. When you type a basic command like cat test.txt, the system kicks off a really precise chronological sequence. Step 1, it searches the directory to find your human-friendly file name. Step 2, it translates that exact name into its corresponding hidden inode number. And Step 3, that inode tells the system exactly where the data lives, allowing the kernel to just fly across the physical disk, scoop up the right blocks, and throw the file onto your screen. Your read speeds rely so heavily on how efficiently these inodes are structured.
All right, Section 3, deletion and stability secrets. Let's shift gears from how files are read to how they are destroyed. Let me paint a picture of a classic server horror story for you. You log into your server, alarms are blaring because the disk is at 100% capacity. You track down this massive log file eating up all the space, and you type rm huge log to delete it. Boom, it vanishes from your screen. You breathe a huge sigh of relief, you check the disk space again, and no way, it's literally still 100% full. So what just happened?
The answer to this crazy mystery is a brilliant little mechanism called the reference count. Remember how we said the file name is really just a sticky label for the actual inode? Well, when you delete the file name, you are only peeling off the label. The underlying inode is only truly freed, and that disk space actually released when its reference count drops all the way to 0. If an active program, like an Nginx web server or a Java database, is still holding that file open, the inode stays totally active. That space will not be released until you restart or force that specific program to let go of the file. This exact mechanism is a massive part of why Linux is just so incredibly stable.
And hey, speaking of stability, let's solve our opening mystery about those power outages. Older file systems used to be absolutely terrified of sudden blackouts because a half-written file could easily corrupt the entire drive. To fix this, Linux popularized something called the journaling mechanism. Before the file system actually writes your data to its final destination, it quickly jots down its intent in a dedicated journal. So, if someone literally trips over the server's power cord mid-write, no problem. The system just reboots, reads the journal, and replays the exact operations to repair itself automatically. No corrupted drives, no ruined weekends.
Next up, Section 4, Common Linux File Systems.
One of the absolute greatest strengths of Linux is that it gives administrators the total freedom to swap out the file system engine based on whatever job is at hand. For your standard everyday use, you've got X4. That's the rock-solid default you're going to find on almost every Ubuntu server. Now, for massive data centers, you'd probably pick XFS. If you need fancy, advanced features like instant snapshots, BTRFS is incredibly powerful. And for the absolute peak of enterprise-grade, self-healing storage, ZFS is pretty much the undisputed king. You just pick the tool that perfectly fits the task.
Finally, Section 5, Monitoring and Enterprise Storage.
If you want to monitor these systems like a seasoned pro, you really only need 3 essential commands in your daily toolkit. First up, df-h. That gives you a great bird's eye view of your overall disk capacity. Second, when you need to hunt down exactly which folders are eating up all that space, do-sh provides a super precise breakdown. And lastly, lsblk visually maps out the physical disk structure so you can see exactly which hard drives are plugged in and where they're mounted. Those 3 commands are practically the daily heartbeat of any Linux engineer.
But out in a true enterprise environment, we aren't just messing around managing single hard drives. We use LVM, or Logical Volume Management. LVM acts as this amazing abstraction layer that pools multiple physical hard drives together into one giant virtual drive. Meaning if your server is running out of space on a random Tuesday afternoon, you don't even need to shut it down. You can literally plug a new hard drive into the server and dynamically expand the capacity on the fly without a single second of system interruption. That right there is exactly why Linux rules the cloud.
So as you can see, the file system isn't just some dumb bucket to dump your data into. It is a highly reliable, incredibly efficient architecture. The inodes, the journals, the mounts, these are the absolute bedrock that modern cloud and AI servers rely on to function flawlessly. When you understand the Linux file system, you truly understand the soul of the operating system itself. So now that you possess the key to this hidden world, what complex infrastructure mystery do you want to solve next? Leave a comment down below with the topic you'd like us to tackle in our next explainer. Thanks for joining us.